Hello trigonometry students, my name is Jami Emigh, and this video is continuing our discussion for chapter 2, starting with the example, find all values of theta in the interval 0 to 360 degrees, including 0, not including 360 degrees, that make cosine of theta equivalent to negative radical 2 over 2. All right, we're going to do this using three different tools. We're going to use the unit circle, we'll do the same thing using the table, and we'll confirm our answer using the graph. So here are the three tools, and let's start with the unit circle. We're being asked to address cosine of a certain angle, and we know that cosine is the x-coordinate. So when we go to our unit circle, we want to be looking at the x-coordinates of these quadrantal angles and special angles. So looking at the x-coordinates, we want to find the ones that are negative radical 2 over 2. There's one right there. Keeping our eyes on the x-coordinates. There's another one. X-coordinates. And that's it. So cosine at which angles will have a value of negative radical 2 over 2? Well, if we open our terminal side to right here, 135 degrees, that is one angle in which cosine will equal negative radical 2 over 2. And there's one more that we found here. And it turns out that 225 degrees cosine of that angle will also be negative radical 2 over 2. All right, we're going to use the table now to confirm that. Okay, cosine, so we're using, these are the values right here. So we look for the ones that equal negative radical 2 over 2. Here and here. And now we answer the question, which was what angle measures, or which theta makes cosine equal to negative radical 2 over 2. So we go to the first column for that, and there's one, 135 degrees, and second, 225 degrees. Different tools, same answer. We're going to confirm those, the same answer with the graph this time. All right, so we are following this cycle of cosine of x. Here it's all positive, We need to stop where it equals negative radical 2 over 2. Here it equals 0, continuing. It's right here. If you can see negative radical 2 over 2, that hit, I'm just going to use a dashed line so you can see where my eyes are, right there, where my eyes are looking. So here we have 135 degrees. And cosine of 225 degrees, that also makes the value negative radical 2 over 2. And that's it for our interval of 0 to 360. So confirming 135 degrees as well as 225 degrees. All right, I want you to do the same thing now with this example. Find all values of theta in the interval 0 to 360, not including 360, for sine of theta to be equivalent to negative radical 2 over 2. I want you to use all three, unit circle, table, and graph. Here they are for you. Pause the video and do that now. All right, welcome back. Let's see what you got for your answers. If you put 225 degrees and 315 degrees, you got it right. If not, let me show you where those come from. Sine, using the unit circle first. So we'll be looking at the, not the x-coordinates, that's for cosine. We're going to look at the y-coordinates on the unit circle. So traveling around, we're looking for y-coordinates that equal negative radical 2 over 2. Y. Nope. There's one. Negative radical 2 over 2. There's a second one. Not there, not there. All right, so it turns out that if this is our initial side, opening up the terminal side at 225 degrees, sine will be negative radical 2 over 2, as well as opening up that terminal side to 315 degrees. Sine will be negative radical 2 over 2. Let's confirm that using the table. Negative radical 2 over 2 is here and here, confirming our angles theta could be 225 degrees and theta at 315 degrees. And using the graph, we want negative radical 2 over 2, so that's here this time. And just using this dashed line to show where my attention is going. Right here, this is at 225 degrees, and then the function hits that value, negative radical 2 over 2, again right here at 315 degrees. All right, our unit circle and our table, those contain the exact values for the special and quadrantal angles. But to find approximate values for other angles, we're going to use calculating technology. All right, so let's practice with this. Use calculating technology to approximate cosine of 97 degrees. Get my TI-84 out. Cosine of 97 degrees. So I'm in degrees already, so I just do cosine 97 and run it. Output is negative 0.12186 and so on. We're not asked to round it. We're asked to we're not asked to round off to a certain number of digits. So we're going to give everything that we can. My calculator screen gives me this much. All right, next one. We're going to use calculating technology to approximate secant of 97 degrees. Okay, turn to your calculators and you might notice that there is no secant key, and that's okay. We can find its approximate value by using the reciprocal function, which is cosine. It looks like this. You're going to type it in as 1 divided by, so that's dealing with the reciprocal portion, cosine of 97 degrees. And that gives us the value of secant of 97 degrees, which is approximately negative 8.2055 and so on. Looks like that there. All right, next one. It's asking us to use calculating technology to approximate 1 over cotangent of 51 degrees. And again, if you go to your calculating technology, you likely don't have a cotangent function, but that's okay. We know that its reciprocal function is tangent. So we're going to figure out that value using its reciprocal, which would be tangent of 51 degrees. Notice this one was given to us as 1 over cotangent. So tangent of 51 is the reciprocal of that. Run it and we get approximately 1.23489 and so on. It's a note for you. Next one, use calculating technology to approximate sine of theta equivalent to 0.25. Now this question right here is not asking us to find the value of sine at some angle. It's asking us if the value is 0.25, what is the angle for sine? So we are going to need to take the inverse function to isolate theta. So theta is equivalent to inverse sine, looks like that, of the value 0.25. So typing that in, we need to hit shift first to call in the inverse sine function, value of 0.25, close it, run it, and theta, or the angle, sine at approximately 14.4775 degrees has a value of 0.25. Type it up, looks like that. And part E, same thing. Theta is the unknown this time, so we are going to use the reciprocal function, but we have another issue. We don't have a secant key either, so we can't just use the inverse secant function. So instead, we're going to have to use cosine inverse, and we're going to make sure to do that of the reciprocal of this value right here. So instead of 1.5, we're going to do cosine inverse of 1 over 1.5. It looks like this. Close it, run it, and it turns out that a cosine of approximately 48.1896851 degrees will have a value of 1 over 1.5, which makes secant of that angle having a value of approximately 1.5. Move this over here for our last one. All right, last one is asking us to find sine of negative 246 degrees. Seems pretty straightforward, but I do want to show you one common error, and that is to hit sine, and then instead of using the negative, which is here below the 3, it would be wrong to use the difference function right here. So make sure you use the negative below the 3, then your 246 degrees, close it, run it, and you should get approximately 0.91. Okay, if you are getting an error, it is most likely because you're using the difference function or the subtraction key. You want to use the negative key instead to get your approximate 0.9135454576. All right, and that is how we find approximate values of trigonometric functions that aren't on the unit circle necessarily, or our table, or easy to identify from the graph. We can approximate them using calculating technology. Here we have an example. An automobile traveling uphill or downhill experiences a force due to gravity. This force, noted as capital F, in pounds, is the grade resistance and is modeled by the equation F equals W sine of theta. That's where theta is the grade and W is the weight of the automobile. If the automobile is moving uphill, then theta is positive or greater than 0 degrees. If the automobile is moving downhill, then theta is negative or less than 0 degrees. And you can see those two situations here. We're going to do an example that works with each right now. Part A asks us to calculate that grade resistance F to the nearest 10 pounds for a 2,500 pound car traveling uphill with theta equal to 2.5 degrees. So that's this situation right here, traveling uphill. So initial side, terminal side, theta is positive, and we can find that grade resistance using our formula F equals W times sine theta. So let's take our calculators out. And typing that in, we start with the weight of the vehicle, which is 2,500 pounds. We multiply that by sine of the grade, which is 2.5 degrees in this one. And it turns out that we have a grade resistance of 109.048 and so on pounds. We are asked to round to the nearest 10 pounds, so this is closer to 110 pounds. So that solution would look like this. All right, part B is for a 5,000 pound truck traveling downhill with theta equals negative 6.1 degrees. So that's like this scenario here. Initial side, terminal side is below that. So we have theta being less than 0 degrees. So we're going to start with the weight of the vehicle, which this is a truck that weighs 5,000 pounds. Multiply it by sine of the grade. Make sure you use the negative 6.1 degrees. Close it, run it, and this time we have a grade resistance or force due to gravity of negative 531.32. So rounding to the nearest 10 pounds, that would be approximately negative 530 pounds. Now, forces, think of vectors, which have magnitude and direction. So this negative is showing the direction, and the 530 pounds is the weight. All right, part C wants us to discuss and calculate that grade resistance if theta were equal to 0 degrees and if theta were equal to 90 degrees, and explain those values. Okay, let's talk about the first situation. If theta was equal to 0 degrees, then the road is level, okay, no slope, and gravity would not cause the vehicle to roll. So, using the formula, the force is equal to the weight of the car times sine theta. Well, if theta is 0 degrees, then we're talking about sine of 0 degrees. Sine of 0 degrees is 0. You can get that from your unit circle, your table, your graph, your calculator. So the weight times this 0 is equal to 0 pounds. So flat road, no grade resistance. Let's talk about if theta were equal to 90 degrees. That road is vertical, and therefore the full weight of the vehicle would be pulled down by gravity. So force equals weight. If you're studying physics classes, engineering, you'll see that. Using the formula, it would be the weight times sine of theta. Well, if theta is 90 degrees, then sine of 90 is 1. You can get that from your table or unit circle or your graph. And the weight of the vehicle times 1 is the weight of the vehicle itself. So if the road is vertical or theta is 90 degrees, that grade resistance or the force due to gravity is the entire weight of the vehicle. Last slide, and then we'll take a break for the homework. Further applications of right triangles. When a single angle is given, such as 164 degrees, it is understood that the bearing is measured in a clockwise direction from due north. So look at these four. Which one of these do you think represents a bearing of 164 degrees? It's this one here, the second one. This is the due north, and we travel in the clockwise direction, okay? Let's explore the others. This one is due north, traveling in a clockwise direction. We would have a bearing of 32 degrees. So all of this can be identified by just saying 32 degrees. Bearings are often used when you're talking about navigation. So due north, and then the 32 would go this direction. No confusion that it might open the other direction, okay? Here's another example. There we go, due north, and for bearing, we open in the clockwise direction. So it's a little tempting, especially for this one, to take the shorter path to the terminal side, but in bearing, we don't do that. Due north, measured for the initial side, and then clockwise for the terminal. Last one, again, might be tempting to go this direction, but for bearing, due north, terminal side opens in the clockwise direction. Here's an example of bearing. Radar stations A and B are 3.7 kilometers apart. Station A detects a plane at point C on a bearing of 61 degrees. Station B detects the same plane on a bearing of 331 degrees. Let's take a look at that here. Here's station A, and they saw the plane on a bearing of 61 degrees. So we have due north, bearing of 61 degrees opens in the clockwise direction, and so this terminal side intercepts where they see the plane. Station B, same thing, due north, but they set a bearing of 331 degrees. And we don't want any confusion here, so we head in the clockwise direction always for bearing. And this terminal side intercepts the terminal side from station A, and we can identify the location of that plane knowing the bearings from station A and station B using trigonometry. Whoops. So we're going to pick an interior angle. I'm going with the 29 degrees. I'm going to use cosine because cosine of 29 degrees will be equal to lowercase b, which is what we're being asked to find, the distance from station A to the plane, over the hypotenuse of the right triangle. It looks like this when we translate it into a trigonometric equation. And now we just need to use our algebra skills to isolate that unknown. So multiply both sides by 3.7, and it turns out that the distance from station A to the plane is 3.7 cosine of 29 degrees, or approximately 3.2 kilometers. All right, let's stop now and do some of our homework. I want you guys to please do numbers 17 through 25. All right, my name is Jami Emigh. Thank you for being here, and I will see you next time.